So this talk is Andy Palmer and Matthew. Is Matthew here? Matthew Hapsey? Matthew Hapsey.
Hi, Matthew. Nice to meet you.
Paul Reisber as well. Paul, major contributor to this. Henry Roseberg, who I think is online, and myself. So we'll be doing a little bit of a double act. Many thanks also to Rob Mahoney's System Theory and Robotics Lab for their support of this work. Over to you, Andy.
Thanks, Tridge. So look, Tridge has really covered the acknowledgements, but I think, again, I'd just really like to thank Andrew Tridgell for allowing this project to come to life. Without his tireless efforts, we wouldn't have got there at all. So I'm going to give a bit of an update on the Ardupilot Autonomous Aerobatic project. So I guess we could start off with defining maybe what aerobatic flight is. With Ardupilot, I think most of the time we're trying to avoid aerobatic flight. So aerobatic flight is where we intentionally take the aircraft into an abrupt maneuver or into a funny or strange or abnormal attitude. So normally with Ardupilot, we're trying to limit pitch and roll angles, maybe roll angles to 45 or 60 degrees, pitch angles below 45. But with aerobatic flight, we're exceeding those on a frequent basis. So a little bit of a warning, aerobatics can be addictive. So if you guys try this, you're likely to want to try it more. Of course, the fine print, you do need a suitable aircraft, and you've got to be on the lookout. Behaviour might not quite be as expected. So what I'm going to talk about today, firstly, just to remind us why add autonomous aerobatics to Ardupilot. I'm going to give a brief recap on year one, then describe what we've done in year two, and then a few comments about what we're thinking for the future. So why autonomous aerobatics? So adding the possibility of doing aerobatic flight with Ardupilot is a really cool thing for the average modeler or person interested in autonomous flight, to let them demonstrate something really interesting to their mates. So they can fly along and do a loop, even if really they're not confident enough themselves to do a loop. There are also potential uses in more serious applications like collision avoidance and upset recovery, and also perhaps like in stall recovery. With the autonomous aerobatic project, we're already into the realm of stall maneuvers, doing stall turns. Eventually, we'll be doing spins and snap rolls, and they require recovery from stalled flight regimes. And that may be of interest for the more general community if the aircraft ever got into those situations. My motivations, though, were something just a little bit different. So I'm an aero modeler. I have been forever. And my big interest is a class called F3A, which is a international aerobatic class. It's judged by a panel of 5 to 10 judges. The schedule is the same each time. It runs for 2 years, 17 manoeuvres. But how do the judges know what the manoeuvre should look like? And in fact, how do pilots know what a manoeuvre should look like? I don't think any of us prior to this project had ever seen a perfect loop performed in front of us. So the idea was, if we could have an aircraft flying aerobatics autonomously, a group of judges could watch that aircraft and discuss how the aircraft performance that they're seeing autonomously compares to what they're trying to judge. And from a pilot point of view, we could watch 100 or 200 perfect flights and then try and replicate that. Of course, also for fun. So this is an example of a typical F3A aerobatic schedule. I guess if we were looking down on this, and this was looking down from the top, you'd think, well, okay, we can sort of fly that already. But of course, this is all in a vertical plane, and I'm sure you can appreciate Ardupilot with the current mission planning and control couldn't achieve this. And but this is now the sort of thing we can do under the autonomous aerobatics. So in year one, we started off by adding a yaw rate controller and added that to the auto tune. And we implemented rate controlled loops and rolls. And basically, this was a bit of akin to a blind pilot flying along and doing a loop by pulling on the elevator and waiting until they were level again and letting go of the elevator. There was no accounting for wind drift, etc. There was no path or trajectory to follow. And also in this implementation, our hands were tied by gimbal lock and, of course, the lack of navigation during the maneuvers. So we knew that from the start, but this was a really good way of getting going with the project. So in year two, though, we've done some really exciting stuff. So we started off by adding quaternion navigation, and thank you to Matthew for that. That was with his great efforts. And having implemented quaternion navigation, we needed a way of designing maneuvers. And again, with Matthew, we spent a lot of time starting off using a very complex method of defining maneuver paths. But as you'll see, that's now become very simple. We needed a way of linking maneuvers together. So after we'd designed a loop and had the path for that, and we wanted to do the next maneuver down here, maybe a stall turn, we needed a way of linking the two together and forming the schedule of maneuvers. So we did that, and thanks to Tridge, that ended up being an exceedingly simple way that end users can understand. And as I've already mentioned, I thought it was always going to be really interesting to add some maneuvers outside the normal flight regime, and we've so far added stall turns. And I'll also talk a bit about dual or formation aerobatics, which we've already demonstrated here this week and will again this evening. So our maneuver design, just briefly in year one, I've highlighted really sort of the important bit of code here. By the way, this is all done within a Lua script. So there were C++ code changes in the beginning to let us do the quaternion maths and manipulation, but the aerobatic code is really all done within Lua. So in year one, just this line highlighted, just sort of demonstrated if we wanted to do a loop, we set the throttle, we demanded a pitch rate, and for a loop, it would be a 0 roll rate and a 0 yaw rate, and that's what the aircraft did. So Euler angles, to do anything more fancy, those started becoming a limitation, and we knew that would be the case. So Matthew implemented our quaternion navigation for us. And after that was there, we needed to figure out a way of defining maneuver paths. So the Desmos website was used a lot, spent a lot of time looking at that. And as you can see, some very complex equations. It was always going to be out of the realm of what the average user or even the advanced user could do. You know, to even just do a loop was relatively complicated. And after we had a path defined in Desmos, that still had to be transported or transferred into our Lua script as some sort of code. So this bit of code here is simply doing a vertical box, which might be a square, just simply 490-degree corners connected with some bits of straight flight. And I've highlighted just one small bit of this, really too complicated for anyone to make head nor tail of. Mm-hmm. And at this stage, I was thinking, well, you know, we could define a whole lot of maneuvers, but that limited people to only using the maneuvers that we had defined. And, you know, Fridge, of course, was aware of this. And so our next step was to take this, which really allowed us to test our path following in SITL and, in fact, in real life. And And once we had that going and we knew that we could do this maneuver, it was then a case of just going backwards a little bit and go, well, how can we do this maneuver in a simple manner? So this is where we are at the moment. So this is an example of an Immelman turn. So the maneuver description's on the left there, and that's a bit of code in Lua. Maybe you don't know what an Immelman turn is. It's simply a half loop, which you end up high inverted, followed by a half roll back to upright flight. So the maneuver definition there, you can see we do a vertical arc, and it's a defined radius, and it's through 180 degrees. And we don't want any roll going on because it's a half loop. We want the wings to be level. So that's what the first line in bold there tells us. And then the second line in bold there, we want to do this half roll. So we give a length over which the half roll is going to happen. And here it happens to be the radius divided by 1.5. And through how many degrees do we want to roll? So we roll through 180. And by miracle, we end up back in level flight up higher. And so this gave us a method of really simply designing maneuvers. And just briefly, another example of the maneuver definition, this time a maneuver called a Cuban 8. And you can see in bold, just very briefly, we start in level flight, we fly a short length of level flight, we then do a 5/8 inside loop, which is a vertical arc through 225 degrees. We then fly a short bit of inverted flight on a 45-degree downline. We don't need to tell it it's on a 45-degree downline. It already knows because we just did this 5/8 loop. We then do a half roll, followed by another segment of straight flight, and then a 3/4 loop, then the same down leg repeated with the straight flight, the half roll, the straight flight. Then finally, a vertical arc through 45 degrees, which puts us back on level flight. So the path following just takes that quite simple code that I think most users could understand if they wanted to define their own maneuvers, and uses the aircraft, for example, in this maneuver, the ailerons to keep a 0 roll rate where required, to do the 180-degree rolls where required, but otherwise using the elevator and rudder to guide the aircraft through the path. So having figured out how to do these maneuvers, we then said, well, if we do just one loop, that's fine. But of course, that's a little bit boring. Who wants to do just one loop? We want to do a schedule of maneuvers and link them together. So we wanted, again, to make that really easy for the end user. And as we've been going along with this project, I think Tridge has learned a lot about aerobatics and how competition aerobatics is flown. And we fly in what's called an aerobatic box, which essentially, if you're standing on the flight line looking straight out from you, you could imagine a center point straight out from yourself. 60 degrees either side of that center point are the extremes of the box, and also 60 degrees vertical. And the idea is we fly on a flat vertical plane 150 to 175 meters out from ourselves. So we know, my next slide probably where we start the mission, but when we start the mission, we start it typically on that center point. And when we do the first maneuver, we want it to start on center. So simply putting a line center in this is in fact done in a text file. So this is actually outside the Lua script. So the Lua script includes the maneuver definitions. Once you've got those, it's just a simple text file to define the schedule. So first maneuver here is starting on center. So that's what a line center tells us. The message comes through on Mission Planner as sound to tell us what the maneuver is going to be. And the third line there tells us the next maneuver is going to be a scale figure 8 with a negative radius. So negative being a left-hand radius, and a negative bank angle, which is a left-hand bank angle. And after we've done that, we want to do the next maneuver at the end of this imaginary box. Early on, I was calculating how much straight flight I'd have to fly before doing the next maneuver. For an Immelman turn, we now know what an Immelman turn is. It's a half loop with this half roll at the top. That's quite easy to figure out how much straight flight you need to do so the end of the manoeuvres at the end of the box. But with more complex manoeuvres, it was quite some calculation to figure out from when the manoeuvre started to start at the right point so that the far edge of it would be at the end of the box. But with this align box command, that automatically calculates how wide that manoeuvre is. So the aircraft will fly in straight flight till it gets to that point, and then do the Immelman turn, putting the edge of the half loop right on the edge of the box. So that's really powerful. And out of interest, the box width, that's defined as an Aero M parameter. So we can say we want a box width of 400 meters or 500 meters, and then the text file then respects that and uses that width. And then after the Immelman turn, next maneuver we might want on center again. So it's simply align center and then give some parameters for the next maneuver. So really powerful. We can align box to a number less than 1, which will make the edge of the maneuver not all the way to the edge of the box, and that's really useful at times as well. Also, as an Aero M parameter, we can scale the whole schedule, make it all bigger or all smaller without changing any of these radii, and also reverse the direction of the schedule by just putting a -1 or making the scale value negative. Right, so I briefly mentioned on the last slide just that how do we start to find where the schedule starts? So we use Mission Planner, and basically you can see waypoint 4 here is straight out from the pilot, and it happens to be 150 meters out from the pilot. When the aircraft hits waypoint 4, you can see there I've given an acceptance radius of 1 meter. So that means the aircraft's got to get right to waypoint 4 before doing anything. And once it gets to that acceptance radius of 1 meter, it then comes down the waypoint list. If it sees waypoint 5 is to run a script time function. And here I've used the number 99, which means it will run trick 99 out of our text files. And that's an aerobatic schedule. It respects the starting altitude. So here I've set 70 meters. So we're coming along at 70 meters. It hits waypoint 4, then runs the waypoint 5 command script time and starts the schedule. Just very briefly, one really interesting thing we struck is once this was all up and running, I was looking at these schedules we'd flown for real on a viewer, and I noticed that the start point, if we had a loop at the start of the schedule, that the start of the loop was offset by maybe 10 meters or maybe even a little bit more from center. And I couldn't figure this out with an acceptance radius of 1. We should have been starting right on center. And this wasn't really seen in SITL. And I talked to Tridge about that, and Tridge went, yeah, it's not starting on center. Why is that? And with a bit of cunning detective work, Tridge realized that once we hit this acceptance radius, we were actually doing a lot of processing within the Lewis script, looking at this text file, loading it all up and setting it all up to start the schedule. And it took about 0.3 of a second for those calculations and things to happen. And we're flying at about 30 meters per second. So that was our 10-meter offset from center. So now what we do is do all those background early calculations well before we get to the nav script time function. And so that means once we hit center, it already knows what to do. It knows how long the schedule is going to take. It knows the path length, and bang, it's underway. And suddenly all our center points are suddenly matched up in our viewer. So, so that was a really, really nice find. Of course, like probably any project in ArduPilot, things don't always go as expected. I could put up, I think, hundreds of slides like this. On the left, that was a first go at doing a square loop. Doesn't quite look like a square loop. And of course, the graph on the right could be tuning parameters, could be a whole lot of things. Probably you could say they're supposed to be straight lines and they're not. So it was just really interesting early on, and just showed how valuable SITL was as a way of figuring out what was going on. And without SITL, this project just couldn't have happened at all. And I think the 6 stages of debugging were mentioned more than once. And on the right, these were early attempts at doing barrel rolls. And I think Paul saved us on that occasion. So yeah, it was great fun to go through and figure out what was happening. And of course, eventually we got it right. So this is a 3D representation of an actual real aerobatic flight. This was flown at a field in New Zealand. I'm using an older, but nevertheless an F3A aerobatic model for this. And you can actually see here, perhaps, there are 2 paths showing the actual and desired path. And they only diverge on very rare occasions. Our path following is really plus minus very much single digit meters, really 1 to 1.5 meters. I mean, it follows a trajectory with remarkable accuracy. And in case you're interested in this way of viewing flights, so this is just a standard ArduPilot bin file, website flightcoach.org. You can load up your bin file and look at a flight with 3D representation, which includes your role and pitch angles of the aircraft. You can bring up a 3-picture display down the left-hand side, and also, as you'll see shortly, play a video through the flight as well, with a little aircraft representing and showing the pitch roll and yaw angles. So, of course, there were more interesting things along the way, and this one to me was very fascinating. And I don't know if Paul wants to say a few words, but I think Paul saved us from the experimental mathematics on this occasion for sure. So climbing 360 with wings level. So if you imagine an aircraft flying along, and then at some point the maneuver starts, we've demanded a certain radius. We've demanded 0 yaw rate, so the wings stay level, and we wanted to climb, say, 40 meters during this 360-degree circle. So the aircraft would start yawing, no problem. It would follow the radius correctly, the yaw path correctly. We would do the climb correctly, no problem at all. But looking closely at our visualization, we'd see that it would come out with the wings, I think, I can't remember, 14 or 17 degrees off,
that's right,
off level. So Paul might like to.
Yeah, so we spent an evening, and I ended up pulling my wife. I ended up.
Let's talk close to the mic
And choke up the microphone. Yeah, so this was very much a passion project for everybody, as in it was evening after hours work. But in this instance, the key was working out that if you took the integral along the path of the body frame and looked at what you required at the end of the trajectory and the start of the trajectory, you realize that you need a particular roll rate. And then we worked that out. And the light bulb moment was that this is essentially the same as a barrel roll, but with a different axis frame. Anyway, that's the whiteboard around about 9 o'clock at night. So I think that's when the penny dropped for that one. So.
And what was remarkable to me,
doing a 360 degree turn
wide climbing up there,
yeah,
like that, but keeping the bank wings level.
Yeah.
So you got to work out what you need in terms of rates. Yeah.
Then we reused the maths for the barrel roll.
Yeah.
And what was remarkable to me is looking at the log files, we saw the wings were 14 or 17 degrees off level. And when Paul, I think there were at least two sides of whiteboard calculation going on, I think.
Yeah.
And when Paul got to the end with a figure, it was exactly what we saw in the logs as to how far off level the wings were.
Yeah. So anyway, it was good fun.
It was absolutely. Thank you, Paul. Stall turns were another really interesting manoeuvre, and I hope things we're learning in the stall turns and hope to learn in the spins and snap rolls will have further application in ArduPilot. You know, ArduPilot works on the basis that it's got control of the aircraft. So there's airflow over the control surfaces. We're going forward, and you know, the PID control loops are all working, and things are good. Of course, in a stall turn, and for those that don't know what a stall turn is, we come along level flight, we pull the aircraft vertical, come back on the throttle, wait for the airspeed to almost decay to nothing, hit the rudder, point the nose straight down, and follow pretty much the same track as we came up, and exit out the bottom at the same altitude but reverse heading to entry. So this was a really interesting one, I think. So how are we going to do things in a stalled condition? And Fridge, I don't know if you want to say a few words just on the stall turns, or shall I briefly?
Yeah, it was dealing with the, the PID in yaw just is really unhappy. And so we ended up with a mechanism of overriding control surfaces within the Lewis script. And also as part of that override, continuously reset the PID that would normally control that control surface. And the trick was getting the correct threshold to the point where the rudder takes control, and then when it stops taking control as the aircraft is spinning around at a particular angle, you start bringing in the PID control again, so it smoothly comes back and locks in exactly at the descending vertical path. And remarkably, if we got it working in settle, then we really were wondering whether we'd be buying a new aircraft for this when we first tried the real one, and it just worked. It did absolutely beautiful stall turns on the real aircraft.
They really are. In fact, this is a real aircraft representation, bin file displayed graphically. And, for me, the stall turn done by this system is as good, but probably better than anything any pilot could do. Like, it really is remarkable. It's very, very cool indeed. So next, I'd like to talk a little bit about our latest addition to the code, which has been the dual or formation aerobatics. So this involved quite a few new components. So we had to have some way of synchronizing the paths between the two aircraft. Collision avoidance, we currently do manually, so that's not included in this. So we needed to come up with a suitable schedule that would mean the two aircraft didn't end up just flying into each other. But we still needed communication between the aircraft so that they would know where they were on the path, so they could remain synchronized, and also some communication down to the ground station. And also, as we were doing this in Settle, to start with, we obviously needed a suitable viewer. How were we going to display these two paths and be able to play through and see how they were looking, which is a very important aspect of any development. So this was from earlier this week, which was after our first go for real with the dual aerobatics. Both aircraft are in one piece. It was remarkably successful. I think better than any of us could have ever hoped in terms of what the aircraft did. So this is just...
The mouse should work.
Yeah. Oh, yeah, thank you. So this is using the Flight Coach code, which is our bin file 3D viewer, which Tridge modified both the viewer, but also created a method of combining two bin files together to let the viewer view both simultaneously. Now, you will have seen they took off one after the other. That was to avoid collision, but they joined up pretty early on in the schedule. and they're forever trying to keep the same synchronization as they fly these maneuvers. There's no master and slave, so the aircraft sort of both masters, as it were, and through the schedule, we've got synchronization points, and the aircraft try and they know how far away they are from the next synchronization point, and if one's ahead, it will try and slow down, the other will try and speed up, so they get to the same synchronization. So you can see here the aircraft just finished doing a loop, and they're tracking pretty closely together. This maneuver is a half reverse Cuban 8.
And this is the real aircraft from the log when we flew it on Monday.
And I've just done a 2-point roll and a half Cuban 8 that time. And now these are the synchronized barrel rolls. These are offset in position, again, to avoid aircraft collision. You can see the viewer lets us rotate around 360 degrees to see what's happening. The next maneuver here is a crossbox top hat. And this is a square loop. You can see they're a little bit out of sync here, but you'll see as they come out, they're trying pretty hard to remain in sync. And finally, needed to figure out the landing. So this is actually the takeoff was not ArduPilot takeoff, it was trajectory controlled using the script, and the landing is trajectory controlled the setup for the landing is trajectory control. So both aircraft back on the ground. So thank you. I mean, it was really cool to watch. It was, and this evening as well. So,
bring it back
yes, I'll bridge if you wouldn't mind.
I'll just bring it back to the slides, and so we are. My apologies. Dual aerobatics slideshow.
So the same thing will happen again after the next one.
Yeah. So we should be able to go to the next slide there.
Yeah. So thank you, Michelle, for this bit of video. She was our videographer for the flights. So this is just very quick, just a few seconds, showing a half reverse Cuban 8 down the end of the box here. So again, that was boxer line 1. It took us right to the end of our aerobatic zone, and we're coming up to do a Cuban 8, and you're all experts on Cuban 8s now because I've gone through that maneuver. So we're going to start with this 5/8 inside loop. So both aircraft are pulling up here. On the way down, short straight flight, half roll straight flight, 3/4 inside loop. And then on the way down, there's going to be more straight flight, half roll straight flight, and then this 45-degree vertical arc to exit. And you can see there that the path synchronization is pretty good. The paths are set up that the aircraft are offset by 20 meters. So they should be both at the same altitude, but 20-meter horizontal offset. So also during year 2, I've done a few demonstrations. As well as aerobatics, I also fly some scale. And my wife was me there with our model that we fly in scale competitions. And so at our national championships, I demonstrated a scale schedule and also our aerobatic clubman sequence, which is our sort of beginner aerobatic sequence. And they were done, and which includes a stall turn, no problems. And these were done in a really strong breeze. And I think the pilots there and the judges realised just how powerful this system is going to be into the future to help with understanding, judging and flying of these schedules. And in fact, following that, I presented to the FAI, which is sort of the international governing body of aero modelling, to their scale subcommittee about this system. And they, I think, realised, much as anything else, their rule book was going to have to be updated because it showed a whole lot of things that they weren't really aware of. And just very briefly, I'm not sure how time's going, actually.
Going well.
Okay, great. just very briefly, one of the scale manoeuvres is a horizontal figure eight. Is that what I'm talking about there? In fact, anyway, in these scale schedules, some of the manoeuvres are flown in a horizontal plane. In fact, I'll take the example of just a simple horizontal circle. The rule book says this should be flown at constant bank angle, constant radius. And what they didn't realize when they wrote these rules is just how uncoordinated the aircraft would be trying to follow those two parameters. So maybe on a calm day, you could pick a bank angle and a radius that the aircraft could fly in coordinated flight during. But certainly with any sort of breeze, if you want to maintain constant bank angle and constant radius, the rudder and elevator are going to be doing all sorts of weird things, and the aircraft's going to be in totally uncoordinated flight to achieve the judging parameters for those sort of maneuvers. And I think that's, created a huge amount of discussion amongst the powers that be, is how do they tackle that? Because up till now, it's not been apparent to them that that's, of course, what the aircraft would have to do. And also for our aerobatics rulebook, very briefly, one of the very interesting things is our rulebook. I've described we fly on this vertical plane or vertical box. When you do a loop in front of yourself, the loop, you can imagine if the aircraft flies a true geometric loop from the point of view of the aircraft, from the ground, it pretty much looks round. But if we fly that same loop at the end of the box, if the aircraft flies a true geometric loop to the point of view of the aircraft, from a ground observer, we're looking at an ellipse, okay, because it's off to one side, it's offset horizontally, it's also actually offset vertically. Our rule book suggests that all our manoeuvres should look correct from the point of view of the pilot or judge. But many people believe that that's not the case. In fact, this project's already shown us that we're flying geometrically correct manoeuvres from the point of view of the aircraft. And when we do a loop at the end of the box, that looks like what the judges are looking for. So it's actually, again, showed the rule book is probably incorrect in this. And one of the projects we've got for the coming year would be to actually fly some manoeuvres, figure out the math to fly some manoeuvres at the end of the box that actually do look correct from the point of view of pilot or judge, so take into account the horizontal offset and the vertical offset. And I think we're going to find they look pretty terrible, even though they are apparently correct.
Like ovals.
Yeah, exactly. And in fact, not only flying ovals, but one of our big four judging criteria is constant speed. And to fly that funny elliptical shape at constant velocity from the point of view of the ground observer is some weird stuff. Like you actually have to be going faster on the horizontal legs, slower on the vertical legs. And it's a strange thing indeed. So I think it's always good to be a little bit disruptive with these things, and certainly this is going to be. So the future. So I'm really keen to do some spins and snap rolls. So those are another two manoeuvres that are well outside the normal flight envelope of Ardupilot, in that, like a stall turn, they're stalled manoeuvres. These two manoeuvres, the aircraft stalled for a much longer length of time, and there's no control in the conventional sense. But hopefully we can monitor the pitch roll and yaw rates fast enough and to understand what we have to do with the controls to both initiate the manoeuvre and then also to stop the manoeuvre and affect recovery. And as I say, I'm hoping the spin recovery in particular could have wider application as an emergency procedure available to all aircraft if a spin developed. We've also found some interesting slipstream effects going on, perhaps not unexpected, but more apparent because of the flight regimes we're in. You could imagine in stable level flight, our yaw and pitch PID tuning is pretty constant, pretty stable. Plot flow over those surfaces is stable at a particular airspeed. But when we pull vertical, and at the top of vertical climb, we're adding more and more throttle to try and keep a constant velocity. And so the elevator and rudder are becoming more sensitive. So we're seeing, particularly on yaw, we're seeing yaw oscillation. And Paul's already done some really nice code that took those effects into account. And we're hoping to develop that further and include that. Also, we're noticing with our path following, we're not anticipating G load coming up. And so we're going to hopefully add some G load control as well to perhaps make the exit, for example, from a loop. So we actually exit truly at the right altitude and don't drop below. And for rolls as well, we notice that as we roll, we're using elevator initially to control altitude. But of course, as we roll, as we approach 90 degrees, at 90 degrees, it's just yaw or rudder that's now controlling altitude. And then as we head to inverted, the yaw and pitch again blend in and out, and we end up using just elevator. We're seeing a few funny things, and I wonder if some sort of G-load control or look ahead could help with just smoothing those bits of flight out. And of course, we've done it with fixed wing. Wouldn't it be cool to do this with helicopter? And I think that's a whole can of worms, but I think really something exciting to try.
I can make a quick comment on that. You're already covered with all the attitude control stuff. The guide and commands will handle all that. You've got a bunch of tools to do that really easily. The trick, the bit that's going to be the trick with the helicopter is the collective control, the TikToks and things
Yes.
like that. The attitude control will be just trivial, but controlling the altitude and the acceleration in that Z-axis I think is where the whole will be.
Yeah, look, and thank you. Yeah, absolutely. And I think also the real pilots, I think, anticipate what's going to be required in the upcoming bit of the maneuver. So just very briefly, a TikTok with a helicopter about for my hands, the rotor disc, and this is the tail, this is the nose. So TikTok can be done actually in any orientation, but if we do one around the roll axis, this is sort of our middle point, and the helicopter's rolling around that vertical point as fast as you can and through as least angle as you can, but still maintain altitude. So how do we maintain altitude? Well, when it's just off vertical, there's a lift component coming from the rotor disc. So we need lots of collective to try and maximize the lift we get from a minimal angle. And the same with an inverted negative pitch, maximize the lift. But we want as little collective as we can, number one, to not load up the rotor disc and decay rotor speed, but also we don't want the helicopter actually physically moving sideways like this, because that's a different maneuver. So we want the helicopter just doing this, just getting enough. And of course, the real pilot's anticipating very much how far they have to roll, how much collective can you punch, and come back through 0 degrees pitch when you're vertical to not load the rotor disc up. So I think all sorts of exciting things to go. Fridge.
One thing for control helicopters, we need to look at the landing detector before we start trying to do TikToks. But that's the one warning I would say. I think it'd be really cool. I think Heli would get like a real boost in terms of some of the functionality for it starts with.
So comment from Matt, just to the audience online, as saying we need to look at the landing detector in helicopters before we start doing TikToks.
But we will avoid landing with the rotor disc vertical. That will certainly.
Should I do the demo, please?
So Tridge is just going to do a bit of a Sittle demo now.
So I'll show you a little bit. This is Sittle using multicast UDP, and we have the two aircraft on the runway here. And the first mission item, it's the same mission that we're running with the two Yak 55s this evening at CMAC and run during the week. So the mission only has the two waypoints, and then it's got a landing which is not used. The two waypoint is script because the takeoff is done using the Lewis script. So it's trajectory, aerobatic takeoff. So it goes out and then goes vertical straight after the takeoff and does the cross box to get aligned. So it might be best if I actually show you this maneuver here. So this is the path that it's going to fly, and this is the path from the recorded from the real yaks. So one yak takes off a couple of seconds before the other, right? And then it does this vertical maneuver at the end, and then moves across into the main aerobatic box, separated 20 meters horizontally. And you can see it's really quite precise, even though this is a real path from the real yaks. If I show you that now in SITL, what we're doing, so if I go all links force, all links auto, I'm just going to get them take off at the same time because they're not going to collide in SITL. But what you'll see is they'll start to synchronize, right? At the end of the top box crosshat, they start the synchronization. And you'll see these name value floats. We've added inter-aircraft communication using Lewis scripting. So the Lewis script on each aircraft is putting a single value, and that single value is related to timestamp markers in the two schedules, saying that before this Cuban 8, we are at timestamp 6. In the other script, we also put a timestamp 6 for where we want it to be at that time. Then this single floating point value is crossing between the two aircraft at 4 Hertz. Then it goes through our jitter correction time domain movement. So it moves the time domains between the aircraft using our standard jitter correction algorithm, and then is able to translate that remote timestamp into a local timestamp, calculate that as a value in meters from the schedule. So it can query the loaded schedule and say, you're at timestamp 3.62, I'm at 3.91. How many meters is that in the schedule? Once it knows that, it's got a PI controller, which to calculate a target speed differential for both of the aircraft, which then draws the aircraft together. And then during the landing, we don't synchronize the timing of the landings, deliberately have them slightly off from each other because landing at the same point on the runway is generally a bad idea. So that's how it's all synchronized. So I'll just show you, you saw this code earlier, the sort of the half Cuban 8 and the Cuban 8. The key thing here is we created this path composition system that can take a method like path vertical arc and can compose it with other methods. So each of these methods has a defined structure which can be nested to an arbitrary level of nesting to compose paths and chain them on from each other where they continue. And that's how you can create these very, very complex schedules. So then what we've got is this text file here, and this is actually a domain-specific language. So in Lua, we wrote an interpreter for this domain-specific language, which describes the schedule. And you see in particular, at the takeoff, we say that's timestamp 0. So it's marked as timestamp 0. The top hat is marked as timestamp 1. The loop is timestamp 2. Now, the other aircraft is flying a slightly different schedule because we don't want them to collide. So we had to construct this path. So despite the complexity of this path, they never intersect. Those two paths, those two pieces of spaghetti don't actually intersect at any point. And that's done by keeping these timestamps and markers. So here we have a little message for top hat, then this timestamp 1, then these top hat parameters are different for the two aircraft because the top hat crossbox maneuver, it is to get them 20 meters separated on the flight line in the aerobatic box. And so they've got different values here for that top box. There's one of them. And if I go to the other, you see it's a -60 versus a -80. And that's so they end up 20 meters apart. Then all the rest just chains on from that. So we then have all of these maneuvers, the messages, so the ground station announces what it's doing. We've got a special thing where an at the start of a status text means announce as speech. And in the Lua script, we've got an option that the announcements add an at the front. And so then MavProxy knows to announce that. Nice feature for Mission Planner if we can support that at for the announcements. And then it sets up for landing. And again, it's a different crossbox top hat to realign them back on the runway so the landing comes in correctly. But we have to go a slightly longer distance. So you'll notice that the align box here. So here we're doing an align box 1.3. So we're actually going beyond the bounds of the aerobatic box on this aircraft. And on the other aircraft, we are going to align box 1.5. So that means they're now a 0.2 of the aerobatic box difference in length. So when they do the cross box top hat, one is actually at you see the difference here at the end. That's that gap there, so that they come down for the landings with a difference in position here, which means they end up doing the landings slightly desynchronized deliberately, right? So we don't have quite so many issues of the two aircraft trying to touch down at the same moment. Still possibilities of pilot error. The final flight on Monday evening, I got mixed up between which aircraft was which, and I thought, oh, my aircraft's coming in just a touch high. I'll just do a bit of surreptitious stick mixing, not realizing I was stick mixing the wrong aircraft into the ground. So there's still a possibility. Of course, if I just left it alone, it probably would have been fine. So anyway, the creation of domain-specific languages in Lua. This also added the ability to load Lua scripts from files within Lua. So you'll notice that this schedule includes new Lua functions, like this triangular loop has been added in here. And so the Lua script, which interprets this domain-specific language, recognizes when there's a Lua function embedded in your schedule and says, aha, I need to add that function into my global available functions so that they're then callable later on inside the schedule. And so this sort of domain-specific language is very, very powerful. And I think we'll be doing more of these domain languages in Lua in the future for other projects.
This structure that you mentioned, is it part of the Lua toolkit?
Yeah, so it's a standard function. There's this load function where you can give it a string, which then returns an object which has the function pointer inside it. These ones, no, this is our domain-specific language. We wrote the interpreter in Lua. We could, but this language is easier for people to understand. Andy copes a lot better with this language for creating the schedule than using the Lua functions, right?
At the same time, Lua does give you more, I don't know, like more power.
It does, but you can create Lua functions.
Like add more features.
Yeah. We did think about doing this all as Lua functions down here, but it really was easier. Most of our schedules.
In this way, people can share schedules very
Yeah.
simply. It's just a text file that's shared, and you can have several text files set up.
And it can be, what I'm saying, it can be literally just array of, just array of.
Yeah, but all the parentheses and the commas and that semantic stuff, all those little bits of syntax needed in Lua, end users find that bewildering, right? Whereas this domain-specific language, we have our end users who have actually used and created these schedules have found it really, really easy to work with. Yep. We have, it would be lovely. One thing I'd like to do is in this viewer, be able to open an editor box within it and type the schedule in here and have it in real time update what it looks like, right? Now, There is another system for this GUI editor for aerobatic schedules, but it doesn't represent it in 3 dimensions like this, which we could potentially use. But just being able to type in the schedule, having it represent, what we need is to take our Lua path evaluation function and put that into JavaScript so that we could then type a schedule in here and instantly update and show what path it will follow. And that would be an incredibly powerful thing to do. We just need somebody with a bit higher level, bit better JavaScript skills than I have. I managed to do this dual path stuff in JavaScript, but it involved a lot of swearing.
Just on the actual path creation, have you considered having like spline creation as part of it?
So question was, have we considered adding spline creation to the paths? We could do spline, but splines wouldn't meet the types of aerobatic maneuvers that the F3A aerobatics wants. They want very, very crisp, and they're not trying to sort of, minimize acceleration or that sort of thing. Basically, F3A aerobatics tells physics to go and take a running leap. And, it says, physics no longer applies here. The aircraft shall follow this path. And it's a very geometric path. Whereas a spline has a geometric definition, obviously, but it wouldn't look right from an F3A point of view. So we were really creating something that was and Andy's input here as a top-notch F3A pilot was absolutely essential when I often suggested things just like those types of things. And Andy says, no, that is not how it's done in F3A. And we tried to keep it pure within the F3A, constraints to make sure that it's going to produce something that is relevant for that community. All right, I think there may be lunch waiting up the back. So any final questions before we close up for the Saturday morning session? So doing it inside something like Mission Planner, we'd need an interpreter for this. If we did say a JavaScript interpreter of this for the online, there would be the potential to then, have that loaded somehow in C# inside Mission Planner. It's a lot of work, and very few aircraft are going to want to do this. I think it will get more mileage out of an editor in this viewer here than we would in Mission Planner. We have had people creating their own schedules very successfully. And it's so, because you can run Settle with like a 30 times speed up, you create the schedule, right? Go, view. It's actually a very fast feedback loop, very, very fast. And that's already been incredibly successful. So is there commercial interest in this sort of thing? Somebody suggested this could be used on a commercial UAV to scare eagles off that are attacking your aircraft or something, but that's we haven't really discovered any commercial use. This was really just for fun. This was a passion project, as Paul said, and it was just... If somebody could come up with a commercial use, that'd be great, but otherwise it's just fun. Buzz, question? Okay, so potentially we could do the interpreter of our Lua code in the browser. Yep, I expect it by tomorrow morning, Buzz. Okay, thank you all. So that's the end of this session. And we're going to have lunch, which is the back of the room. And then next talk starts at 2 o'clock.